In this video, we're going to talk about section 6.2, which is on operations with decimals. So that basically means adding, subtracting, multiplying, and dividing. So the goal here is that by the end of this, and by the end of doing your homework, you can fully understand how to add, subtract, multiply, and divide decimals using the traditional algorithm, and then also by doing some other different types of methods like using decimal squares and drawing pictures. So let's start with addition. So we're going to revisit the decimal square, and just to review, the larger square is equal to 1. So this entire piece here, this entire square, that's equal to 1. And then one of the little smaller squares on the inside, there's 100 of them in this picture, so that would be 1/100th. Okay, so let's think about what 0.7 would look like on a decimal square. So 0.47 is equal to 47 hundredths, and the reason I know it's hundredths is because I can count the place values. So we start with tenths place and then hundredths place. So you always go out to the farthest place value that the last number to the right goes to, and that tells you what your denominator is. So we've got 47 out of 100. So you're going to color in 47 squares. So each column is 10. So 10, 20, 30, 40. So I know that I want this, so that's 40, and then you're going to do an additional 7. So 1, 2, 3, 4, 5, 6, 7, and it should look like that. So this is our that's our 0.47. We'll do that in blue, and then I'm going to use a different color for 0.36. So 0.36 is 36 hundredths. So we could draw what 36 would look like on the decimal square. So I'm going to fill in. So we've got 3 here. So that leaves me with 33. And then we've got 3 columns. So that's worth 30. So right now we've got 33 squares, and then I need another 3 to make 36. So 34, 35, 36. You can make it like this. And it doesn't matter how you draw this or what squares you choose. You can make these into different shapes as long as you color in the right amount. So in the end, we've got 47. This is 0.47, and this is 0.36. And then total, we just look at how many squares we have colored in. So we've got 1, 2, 3, 4, 5, and you know what, I probably shouldn't have colored this all in so that we can actually count these. Here, let's do that instead. There we go. So we've got 1, 2, 3, 4, 5, 6, 7, 8 columns, and then 1, 2, 3 extra squares. So it looks like there's 83 hundredths total. Just going to erase this. So it looks like we have 83 out of 100 total, which is 0.83. Now we could certainly line this up. So students start by using pictures, and they do quite a bit with decimal squares first, and then eventually we teach them the standard algorithm, which is to just line up the decimal points, and then we could add and carry just like we would normally if we were adding without decimals, and we get 0.83. Now granted, that's faster, but our goal here is not fast. Our goal is to understand. So let's try this next one. This would be a great place to pause the video and try it on your own. So 0.3 is the same thing as 3/10, because remember we have our decimal place and it's tenths place, hundredths place, thousandths place, like that. Now I have a square here that has 100 pieces in it though. So how do I draw 3/10 if I have hundredths? Well, you could do a couple of things. You could look at each one of these columns as a tenth. So there's 1 column, 2 columns, 3, 4, 5, 6, 7, 8, 9, 10. So I could just shade 3/10 in. Or if you wanted to, you could make 0.3 is the same thing as 0.30. So 30 hundredths is the same thing as 3/10, because these zeros essentially just cancel out. So why don't we write it like that? We can say, okay, well, it's 0.30. Let's write it 30 hundredths. And so we'll shade in 30 of those squares, or 3 rows, 3 columns. Okay, and then let's do the next one. So 0.75 would be 75 hundredths. So then I'll color in, we've got 1, 2, 3, 4, 5, 6, 7. So if I complete this, so 30 and 70 is 100, so that fills up the square, but then I need another 5. So 1, 2, 3, 4, 5. So just like when we add decimals with the regular algorithm, sometimes we could end up having a number that's greater than 1 or greater than 2 at the end. So let's look and see how many squares we have altogether. So we've got 30 here. That represents 0.30. We've got 75 squares here. That represents, well, actually that's 0.7, and then here's 0.05 right there. So all together we have 1. So this whole square, remember over here when I started I said the whole entire square is 1. So I've got 1, and then this leftover is 0.05. So my answer is 1.05. So this is a really good visual of why 0.3 plus 0.75 spills over 1. You can see that it's filling up one whole square and then going a little bit extra. The other thing you can do, if it wasn't clear to write these extra 5 squares as 0.05, you could also write these as 5/100ths, since we have 100 squares, and then that might help you write it as a decimal, because you can think of your places as tens place, hundredths place, and remember, if you just have one digit, you're going to put it all the way as far right as you need to match with this denominator. So tens place, hundredths place, and then you can fill it in with the 0 there. So that's addition. Let's talk about subtraction. So there's a couple different ways you can use decimal squares to illustrate subtraction. So one of them, I just copied this from the book because it was a good picture. One of them is called the takeaway. So take this example right here. Basically what they did was they draw, so you draw the first number, 0.625. So that would be 625 out of 1,000. So the 625, I'm just going to highlight this in blue. That would be the picture that I shaded in blue. And then what we can do is we can take away, if we have to take away 238, we can take away 238 of those squares. So this is 238 is the green part. And then when you take it away, you can identify what you have left. So the leftovers are right here. And there is 0.387 or 387 left over. So that's one way that you can use a picture. Now I think with the squares that have 1,000, I think it's definitely trickier because those are teeny tiny squares. Keep in mind that you could do this much simpler, much more simply by just using a decimal example where you just have 2 decimal places like we did above. And then let's look at the second way that you can subtract. So comparison and missing add-in. So this is similar to when we talked about this, you know, when we were just looking at integers and whole numbers. So if we want to do 0.75 minus 0.4, what we could do is we could draw 0.75. So that's what we did up here. So this piece here, this is 0.75. Okay. And then we draw what 0.4 would look like. So this is what 0.4 looks like. And then you ask yourself, okay, comparing these two pictures, how much more is in the picture with 0.75? So if we compare them, what is this extra piece that 0.75 has? And that's going to be your answer. So there's 0.35 left over. So you can actually, instead of writing it as 0.75, you can think of it as, oh, well, there's 0.35 here. And then there's 0.40 there to make 0.75 altogether. And honestly, when kids are doing this in the beginning, they're just really counting squares. So they're matching up the squares that match, and then they're counting all of the extras. And if there's 35 over 100 extra, then that means when we subtract, the answer is 0.35. So now that we've seen those, let's talk about the paper and pencil algorithm. So this would be, you know, oftentimes the faster method, not always the best method, but it just depends on the person. But one strategy to help students do this is to provide grid paper so everything can be lined up, because it's hard, especially if the kiddo doesn't have great handwriting, it's really hard to make sure that everything's lined up. So the goal is you always line the decimal points up first, and then you could add and subtract as usual. And then if you ever don't have, if there's ever like a gap where the decimals don't line up, you can add zeros as placeholders anywhere to the right of the decimal. So for this first one, 62.47, I'm just going to write 62.47. I'm noticing that both of them have two numbers after the decimal, so I'll put the decimal for the second number here, and then 114. And then we're going to add these together. And I'm going to add just like I would without the decimal places, just I'm going to carry those decimals down. So 7 plus 6 is 13, carry the 1. 8 plus 4 is 12, plus 1 is 13, carry the 1. 4 plus 2 is 6, plus 1 is 7, 6 and 1 is 7, and then I carry down the 1. So 177.33. Okay, let's do the next one. So this one, notice there's 3 numbers after the decimal place there, and there's 4 numbers after this one. So I'm going to draw the one with the 4 numbers first. So 7490, and put my decimal place. So that way I've got enough room in my grid. And then I'm going to write 0.402 there. And then I do have that extra space here. If you want, it's optional, you can put a placeholder 0 there just to make everything line up, so every number has a pair. So now we're gonna add. So 7 and 0 is 7, 4 and 2 is 6, 9 plus 0 is 9, 4 plus 0 is 4, and then carry down the 3, and we've got 3.4967 as our answer. All right, let's try some subtraction. So these two both have 2 decimals after the 2 numbers after the decimal place, so that's nice, those line up. And then I'm going to subtract, so I can't do 2 minus 7, so I'm going to borrow. I'm going to cross this 3 out and make it a 2, which sends a group of 10 over to the 1's place. So 10 plus 2 is 12, which is why I can just put a 1 there. 12 minus 7 is 5. 2 minus 4, I can't do that, so I'm going to borrow. And I'm going to send a group of 10 over here. So instead of 2, I now have 12 there. So I'm going to do 12 minus 4 is 8. And then 5 minus 8, I can't do that. So I'm going to borrow. I cross this 4, make it a 3. I send a group of 10 over. So that makes that 5 a 15. So 15 minus 8 is 7. 3 minus 1 is 2. And you're left with 27.85. And then last one, it looks like these both have 3 numbers after the decimal place. So 493, I'm just working backwards so I know where to put all of my numbers in the grid. And then 6, 7, 8. And then I'm going to subtract. So I can't subtract here because I don't have enough, so I'm going to borrow 1 and send a group of 10 over. So the 4 becomes a 14. So essentially when you borrow, you're always adding 10 to the place to the right. So 14 minus 6 is 8. 8 minus 7 is 1. I can't do 3 minus 8, so I've got to borrow 1 from the left, and then it sends 10 over here. So 13 minus 8 is 5. I carry down those decimal places, and then the 2 just comes down, and this 2 just comes down. So I'm left at 22.518 there. Okay. So now we're going to move on to multiplication. So we're going to think of multiplication as repeated addition, just like we did with whole numbers. So for example, if I have the problem 2 times 3, it means I'm going to take 3 and add it twice. So 2 groups of 3. Well, the same thing is true here for 2 times 0.7. It's the same thing as 0.7 times, or not times, 0.7 plus 0.7. So 2 groups of 0.7. So I'm going to draw 0.7, so that would be 7 of these blocks, or 7D. So 7 would be, you know what, let me back up actually. So 0.7 is 7 tenths. It's also the same thing as 0.7D, which is 70 hundredths. So that's why I circled 7 columns, or 7 of these little squares, 7D of the little squares. So this is 0.7, that's 0.7, and then I'm going to do it again. So I'm going to do, I've got 3 here, so that would be 30, 40, 50, 60, 70, and then that's going to be another 0.7. So then what I do to find my answer is I say, okay, well, what do I have all together? So this whole block is going to be 1. And then I've got 1, 2, 3, 4 rows or 4 columns, 40 of those little squares. So 40 of those little squares would be 40 over 100 or 0.40. So my answer is going to be 1.40, or I could also write it as 1.4. So that's an either or. And then next, let's do one where we've got some multiplication where we've got decimals in both numbers. So we're going to look at this multiplication sign and interpret this as the word of, and that's the same thing we did here. So we're saying 2 of 0.7 or 2 groups of 0.7. So in this case, I'm going to take 0.2 or 2/10 of 3/10. So 2/10 of 0.3 or 3/10. So I'm going to first draw 3/10. Okay, so that would be 3 of these columns because there's 10 columns altogether. I could also write it as 30 over 100. That would also work. So I'm first going to do that. So I'm going to draw 0.3, and that gives me the 0.3 right there. So this whole thing is 0.3. And then my next step is I'm going to break into 10. And I'm going to shade 2/10, so 2 of those 10s. So an easy way is to just break it up this way. So I could break it up in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 little rows there, and so I want to shade 2 of them. So I'm going to get a different color, and I've got 1 and 2. So let me just back up. So, or not 2/10, I'm going to shade, 2/10. So we want to take 2/10 of 3/10. So I drew 3/10 and then I'm going to shade 2/10 of it. And then for my answer, I just need to interpret, well, how many blocks or how many of these little squares did I shade? I shaded 1, 2, 3, 4, 5, 6 of those little squares, and there are 100 of them total in the picture. So my answer is 6/100. And then if I want a decimal for that, I can just go out to the 100th place, so 10ths, 100ths, and I'm going to put a 6 there and then a placeholder 0. So 6/100 is the same thing as 0.06. So either one of those will work as the answer. And then let me show you the other method that you can do is with a rectangular array. So just like I'm going to back up and show you just a reminder. So if I do a rectangular array for 7 times 5, for example, I could draw a rectangle that's 7 in one direction, 5 in the other, and then I actually have to make sure there are 7 blocks in that one direction. So 1, 2, 3, 4, 5, 6, 7, and then I'm going to do it in 5 in the other direction. And then for my answer, all I have to do is count the number of blocks on the inside, and if I count those, there's 35 squares on the inside, so that gives me the answer. So I'm going to do the same thing here. I'm going to draw a rectangle that's 2.5 in one direction and 1.6 in the other. So it's going to look kind of like this. So this would be, and then I'm going to count what's on the inside, and that's going to give me my answer. So the first question is, well, how do I draw 1.6? So how many boxes up do I need to go for 1.6? So let's think about, remember that one of these 100 10 by 10 squares is 1. So a 10, I'm just going to draw this over here, a 10 by 10 square is equal to 1. So if I want to do 1.6, then I'm going to go the 1, that's going to be 10 squares, and then this is going to be additional 6 squares. So I'm going to draw I'm going to make my rectangle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then another 1, 2, 3, 4, 5, 6. So that's 16 squares total, which is the same thing as 1.6. And then on this dimension, I'm going to do, if I want 2.5, remember for every 10 blocks, 10 little squares, that's equal to 1. So if I want 2.5, that means I'm going to do 20 squares to do 2, and then an additional 5 squares to make 0.5. So in this direction, I'm going to count 25. So 3, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. And then what I'm going to do is I'm going to fill in this rectangle. Okay, and then I can count what's left. And so I can count all of those squares. If you wanted to, one simpler way to do it would be maybe to divide it up to make counting easier. So if you do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so that's 10. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can do, and that should, you got to bear with me, these are rectangular, so that's why this square, this is a rectangle, it doesn't look like a square, but it's 10 by 10, so I know there's going to be 100 there. And then let's do it again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm just doing this to make it easier to count so that I don't have to count every single little rectangle, which would take forever. So if this is 100 and 100, and over here I know that this is 6 and this is 10, so I know this is going to be 60. And this is 10 and this is 6, so this is going to be 60, and I can break it up like that. And then over here you can just say 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5. 6 times 5 is 30, and then we've got 1, 2, 3, 4, 5, so this is 5 by 10, so this is going to be 50. So then I can add it all up that way. So I'm going to erase this so I can have some more room here. So I've got 100. I'm just going to add all those up. Whoop. My pen is acting funny here. Okay, I've got 100. I've got 100. I've got 60 and 60. And then I've got 30. And then I've got 50. So if I add all of that up, I end up getting 400 total. And then remember, that's, you can write it, that's 400 of those little squares. So those are 400 hundredths. And if you divide, you end up getting 4. So the other way to look at it is each 100 squares, that's 1. So you've got 1 and you've got 2, and then you can kind of piece together these to make hundreds there, and you're going to end up getting 4 there. So and yes, you could absolutely multiply using the traditional algorithm, which we'll talk about in a minute, and that would be faster, but I think it's worth doing these a couple of times. And the other thing to keep in mind is when students get into algebra, particularly algebra 2, so that would probably be 10th, 11th grade in high school, they're going to use rectangular arrays to and actually in algebra 1 and 2, to factor polynomials, to multiply polynomials. This is going to sort of reach into math classes down the road. So it's nice to set that foundation now. So let's go ahead and we're going to jump into the paper and pencil algorithm. So let's talk about how you would do that. So you can do these vertically. So let's do one vertically, and then we'll do one with the lattice method. So one way you could do this is to completely ignore the decimals and multiply just like you would normally. So 2 times 8 is 16. Carry the 1. 3 times 2 is 6, plus 1 is 7. 9 times 8 is 72. Now I have an advantage here. I can just kind of write over that. You want to make sure you get rid of your previous carry there so it doesn't mess you up. 9 times 3 is 27. Plus 7 is 34. So I'm going to write down 34. And then I'm going to add all my numbers. So bring down the 6, 9, 4, 3, and then really the only thing new is to figure out where the decimal place goes. And the way you do that is you look at the numbers that are in the problem above, and you ask yourself how many place values are they away from the end of the number. So we've got 1 place there, and then you've got 1 place here. you want to add those together, and that gives you 2. So your answer, the decimal place, is going to be 2 spots over to the left, and so your answer, your final answer, is 34.96. So these up here can be anything. You know, you could have moved 3 places in one place, and then you're going to add 3 in one, and that makes 4. So, you know, it just depends on the problem. And then with the lattice, we can do the same thing with the decimal places, but then if you want to use the lattice to multiply, because I know some people just prefer using the lattice, and actually these are both 2-digit numbers, so I could make a nice square like this, and then I'm going to put 5 and 6, so it's 5.6, but like 56 and 0.35 there, and then I'm going to draw my lattice pieces, and then I'm going to multiply. So 6 times 3 is 18, 6 times 5 is 30, 5 times 3 is 15, 5 times 5 is 25, and then I bring down all of the diagonals. So I bring down the 0, and I add these as I go. So 8, 9, 10, 11 plus 5 is 16. Carry the 1. 1 plus 1 is 2, plus 5 is 7, 8, 9, and then I carry down this 1. So I end up getting my answer. I write down 1960, and then to figure out where the decimals go, you can just do the same thing you did before. So count 1, 2, so that's 2 places, and then there's another place. So we want total 3 places in from the right hand side for my answer. So 1, 2, 3. So my answer is going to be 1.960, or just 1.96 will do. So the purpose of the lattice, again, is just to line everything up. When you multiply, everything has a place to go. The nice thing is when you're carrying, you're only carrying 1 time to each column diagonal, so that you don't run into the issue you do over here where you have to erase your first carry to write down the second one. So there is not one right answer or not one right way to do it. So I think the thing is just being, you know, have an open mind so that we can teach our students to do it in a variety of different methods so that they can find one that resonates with them. So this next part, we're going to talk about multiplying by powers of 10, because man, this is so powerful. I feel like if you can learn the trick of multiplying by powers of 10, it's really helpful just in estimating, you know, in real life, because, you know, it happens quite a bit where, you know, you might have to multiply something, and if you could even just estimate getting close to a power of 10, then it makes it easier. So when we multiply by 10, all you have to do is move the decimal point however many powers of 10 you have. So if there are, more simply, if there are 2 zeros, you're going to move the decimal 2 spots. So 100 times 0.45 is just 45. Here I've got 1, 2, 3 zeros, so this decimal moves 1, 2, 3 spots to the right for 327.14. Okay. So now let's move on to division. So we're going to start with the decimal squares, and then we'll talk about how to do it longhand, and then we'll also talk about powers of 10. So let's do this example, 0.90 divided by 0.15. So 0.90 is the same thing as 90 hundredths. So I'm going to first draw 90 hundredths. So what does that look like? So there's 90 hundredths. And then divided by 0.15 means how many 0.15s can go into 0.9, or we can use the subtraction method for division and just say, well, we'll just keep taking off 0.15 as many times as we can, repeated subtraction. So just so you remember, like if I have 10 divided by 2, I could take 10 and repeatedly subtract 2. So I get 8, and then subtract 2 again, subtract 2 again, subtract 2 again, and subtract 2 again until I get to 0, or as close to it as you can. Sometimes it doesn't work exactly. And then you ask yourself, well, how many times did you take off 2? I took off 2 5 times, so the answer is 5. We're going to do the same thing here. So we're going to see how many times we can take off 0.15. Now 0.15 is the same thing as 15 hundredths, or 15 of these little squares. So I'm going to say, okay, well, I'm going to count 15. So 1, 2, 3, 4, 5, and then this column is 10. So there's one group of 15, and then I'm going to do it again. So 1, 2, 3, 4, 5. Okay, so I did it once, twice, and then I'm going to do it again. Did it 3 times. I'm going to do it again. So 5 times, and this happens to work out exactly, you know, as a whole number. And this is, you know, these are the types of problems that we use pictures for. When they get a little bit more complicated at that point, we just move to the regular paper and pencil algorithm. But it went in 6 times, or you subtracted it. We subtracted it 6 times, so the answer is 6. And like always, you can totally check this with your calculator. Okay, so here's another one. So 0.80. Oh, and this is a typo. We're not dividing by 441. We're going to take this and divide it by 4. So we just did the measurement concept, which means keep subtracting. We're going to do sharing concept with this one. And if you think about it, so we're doing 0.80 divided by 4. If we were to do the measurement concept, we could, but it would take a long time because we would be subtracting 4, subtracting 4, subtracting 4. And you can't really subtract 4 from 0.80 because 4 is bigger than 0.80. So that gets complicated just understanding what that means. So, but we can do 4 groups. So let's draw 0.80. So that's 80 hundredths. So 0.80 is 80 of those squares out of 100, or it's 8 of these columns. So I'm going to draw it like this. So I've got 0.80, and then I'm going to divide it into 4 groups. So I could divide it here, and here, and here, and here. And then I ask myself, how many in each group? Well, there's 20 of these squares, 20, 40, 60, 80. So 20 of those squares in each group, or 20 over 100. So the answer is 0.20. So 0.80 divided by 4 is 0.20. And we can check by adding. We can say 0.20 plus 0.20 plus 0.20 plus 0.20 equals 0.80. So there's my check using multiplication. Okay, so we can't leave division without actually doing the paper and pencil algorithm. So this is a good review for a lot of you, since I'm sure it could be very, you know, it could have been a long time since you've done division with decimals. And if not, if you're great at this, then you could just skip this part. But let's start at the beginning. So when we divide, we always put the first number inside the box. So 154.63 divided by 4.7. And with decimals, you need to get rid of the decimal in the divisor. So the number that's on the outside of the box, we don't want a decimal there. And so what we're going to do is we're going to move it over. And if you remember, that's essentially like multiplying this number by 10. Okay. And if we do that to one number, we have to do it to the other. So we don't actually change the quantities, the quantity of the answer. So you're going to move the decimal however many places you need to get to the end of the number, and then you're going to do the same exact things to the number on the inside. So that basically leaves us with a new problem. So I'm going to write 47 goes into 1,546.3. Okay. Now what I'm going to do is I'm going to put the decimal place up top, and as long as you line that up at the very beginning, at this point you just divide like you normally would. So 47 doesn't go into 1, doesn't go into 15, 47 does go into 154. One way that you can kind of estimate is, I always learned this when I was younger and I've used it since, is you take the 4 and you say, well, how many times does 4 go into 15? It goes about 3 times. That's a good way just to estimate. So on the side here, I'm going to do 47 times 3. And it looks like that's a really good, that's the best place to start, because if I have 141 here, if I had done another 47, it would be too much. So I'm going to write 3 and I'm going to put it over the 4 because I'm the 3 is representing 47 going into 154 3 times. So you always want to line up the answer right above the last digit of the number that you're considering. So 3 times 47 is 141, and then I'm going to subtract. So 4 minus 1 is 3, 5 minus 1 is 4, and then that's 0. So I'm just not going to write anything down. And then I'm going to carry down the next number, which is 6. So I can see over here 47 times 3 is 141. That's too much. So let's do 47 times 2, or you could add it up twice. So if you're not as good at multiplication, you can certainly use addition here. So 7 times 2 is 14, carry the 1. 4 times 2 is 8, plus 1 is 9. So we've got 94 there. So I'm going to write 94. And then I subtract. So 6 minus 4 is 2. I can't do 3 minus 9, so I'm going to borrow and add a group of 10. So that becomes 13. So 13 minus 9 is 4. And then I carry down the 3. How many times does 47 go into 423? Well, I know it's bigger than 4 or 3. I can use my trick. How many times does 4 go into 42? It goes in 10 times. Well, the biggest number that you can write here, the biggest one-digit number is 9. So I'm just going to try 47 times 9 and see if that gives me the number that I need. So 9 times 7 is 63, 9 times 4 is 36, plus another 6 is 42, so I get 423, and it worked out great. Oh, and you know what? I did not write my 2 up top here. I should have written a 2. There we go. And so I'm going to write a 9 here. 9 times 47 is 423, and I'm left with remainder 0. Now, if you didn't get a remainder 0, if you got a remainder that was a number other than 0, you could end up adding. You can always add as many zeros on the end as you need to, and those will come down as you do the problem until you either reach your answer, or sometimes it's possible to get to a point where you realize that your decimal is repeating, and then you can stop and just use a repeating bar to put your answer. So the answer here is 32.9. So I'm going to erase this, so you can pause the video if you need to write this down. I'm going to erase this so that I have some room to do the next one. Okay, so for the next one, I'm going to do the same thing, and I'm going to write my division problem. And I'm going to eliminate the decimal from, probably shouldn't avoid decimals, eliminate it from the divisor, and then I'm going to eliminate it here also. So I move it one spot right, and I move this one spot right. And then what that gives me is, it gives me 2, because that 0, the 0 is unnecessary, goes into 464.830. Okay, and then I'm going to divide. So 2 goes into 4 twice. 2 times 2 is 4. Bring down the 6. 2 goes into 6 3 times. 3 times 2 is 6. Bring down the 4. 2 goes into 4 twice. Bring down the 8. 2 goes into 8 4 times. 4 times 2 is 8. 2 goes into 3 once. 1 times 2 is 2, and you're left with 1 when you subtract. And then you bring down the 0. 2 goes into 10 5 times, and so then I'm left with my answer, 232.415. Just like with multiplication, it's a great idea to use grid paper, graph paper for this, so that way everything lines up. I think it's a huge help, especially to kids. And then last, I don't have any examples here, but I've got this box from the book, Dividing by Powers of 10. So remember that when we multiply by powers of 10, the decimal moves to the right. When we're dividing by powers of 10, the decimal moves to the left. So for example, if I had, I'll just make up example, 46.23 divided by 100, since I have 2 zeros there, this decimal would move 2 spots to the left, and my answer would be 0.4623. Okay. And then we can't skip properties. We went over the properties with all of the other type of number systems. We're going to talk about rational numbers. So rational number, I mentioned this before in the first section, is a quotient. So quotient just means divide by two integers, a over b, where b is not 0, because if b is 0, then you've got an undefined situation because you can't divide by 0. So basically it means a fraction or a decimal. Okay, not all decimals, but we'll talk about that. Next time. But let's talk about all the properties. So closure property. So rational numbers are closed under addition and multiplication. What that means is if you have a fraction, a over b plus c over d, you're going to get a fraction answer. If you have a fraction, I'll just write it like this, forget the a, b, and c, fraction times a fraction, and you know what, actually, to be clear, instead of writing fraction, I'm going to say rational number times a rational number is equal to a rational number. It does not work with subtraction and division. It's possible to get a number that is not rational. We can get what's called an irrational number, which we'll talk about in a later section. But it's basically rational or irrational decimals are decimals that don't have a pattern and don't repeat. So as long as they either repeat or they end, it's going to be a rational number. So commutative property means you change the order in which you either multiply or divide, and multiplication and addition are both commutative. So for example, a rational number plus a rational number is equal to a rational number, and then a rational number times a rational number is going to give you a rational number answer. With associative, it's the same. So addition and multiplication are both associative. So I'll give you a real example here. So for example, 1/2 plus 1/3 plus 1/5 is the same thing as 1/2 plus parentheses 1/3 plus 1/5. So I can change the order of the parentheses and it doesn't change the answer. And then with identity, it's basically the same as what we talked about before. So the additive identity is 0, which means, for example, if you take a rational number like 1/2 and you add 0 to it, the number stays the same. You get 1/2. The multiplicative identity is 1 because you can multiply, let's say, our fraction 1/2 times 1, and it ends up staying the same. So you can multiply any rational number by 1 and you end up getting the same number. And then the inverse property. So every rational number has an additive and multiplicative inverse. And I'm going to come down here and write examples for those. So for example, the additive, we could say 5 plus what is equal to 0. The additive inverse of 5 is -5. So these are additive inverses. And the reason is because they add together to give the additive identity, which is 0. Now with multiplication, it's a little bit different. So if you take 5, you can say 5 times what equals 1. So 1 is the multiplicative identity. And what could we multiply 5 by to get 1? Well, you could multiply by the reciprocal, which is 1/5. So 5 times 1/5 is equal to 1. So 5 and 1/5, those are multiplicative inverses. Okay, and then last but not least, the distributive property, it's the same as before. So just for an example, so if we have rational numbers, maybe 1/2 times 4 plus 3, that's the same thing as we can distribute that 1/2 on the inside. That's the same thing as 1/2 times 4 plus 1/2 times 3. And that's important to know, especially to set up the foundation for when students do algebra and they're left with expressions like this that have some variables in them and they're forced to use the distributive property. Okay, so let's do the last page. So the last page, we've got some mental computations and some approximations. These first three examples, we're given the directions to calculate without the decimal first, then place the decimal points. So this first one, I could do 4 times 22, or 22 plus 22 plus 22 plus 22, which would be 88. So 4 times 22 is 88. And then try to figure out the decimal later. So think of this as, you know, or you could just even use your rule for multiplication. So we've got 1, 2, 3 there. So now we can take 88 and move the decimal 1, 2, 3. So we end up getting 0.088 as the answer for that one. For this one, 0.24 divided by 0.04, just do 24 divided by 4. So 4 goes into 24 6 times. With division, think about it. You could also write it like this. This decimal 0.04 goes into 0.24 6 times. And then if you weren't sure on the decimal, you could actually write it like this. And you can see that if we use our trick of moving the decimal place there on the divisor, then we're also going to do it here. So it's essentially the same thing as how many times does 4 go into 24. And then lastly, we're going to add 35 and 55. So 35 and 55 gives us 90, and then we could place the decimal place where it goes. And if you just visualize or think of those 35 squares, we've got 35 squares and 55 squares, and we have 90 squares altogether, so the decimal should go there for 90 out of 100. Okay, the second part, B, add up. So we did this method before with whole numbers. Basically what you're doing here is you start with one number, and the smaller number, and you add up with increments that are easy to do in your head. So, and actually, you know what, you don't have to start with a small number. So what you could do, this is one suggestion, maybe start with 30.37 and add 0.20. Because that's a little bit easier, because you can just say, oh, 0.37 plus 2, or 3 and 2 is 5. So you're left with 0.57, and then you could add the 0.8 at the end, and that sends you to 0.65. So I know it seems more complicated when I write it out, but when you're actually doing this in your head, even though you're taking some steps, I think I know it can be faster because I do it all the time. So 0.76 minus 0.29. So you could take 0.76 and instead of doing 0.29, just do 0.20. So then you're doing 7 minus 2, 5, and that 6 just comes along for the ride. And then you could subtract 0.09. Now what I would do in my head is I'd even just say, okay, 0.56 minus 0.1 is 0.46, and then I'd add 1 back, which is 0.47, but that's optional. You don't have to do that, but that's another suggestion there. C, we've got some, this suggests substitution. So multiply by an easier number and adjust at the end. So with this one, instead of doing 0.98, and this happens all the time. I mean, think about when you go shopping. So many things end in 0.98, the prices. So instead of doing 0.98, just do 3 times 1, or 3 times, think of it as like 3 times $1. So 3 times $1 is $3, but then that's too much. How much do we need to adjust? Well, what's the difference between 0.98 and $1? The difference is 0.02. So we added 0.02 3 times, and we shouldn't. So we're going to subtract 0.02 3 times to compensate. So we've got 0.02, 0.02, 0.06. The other way you could write it is 3 minus 0.06. And you could write it that way. And then you get 2.94. And if you were estimating, you could just estimate and say the answer is 3, but this is not asking for estimating, so we're writing down the correct answer. Okay, next one. So 102 is really close to 100, so I do 4.3 times 100, which means move the decimal 2 spots right, which gives us 430. And then I'd ask myself, okay, did I do too much or too little? Well, I did too little because I was supposed to have 102 groups of 4.3. So I'm going to add 2 more groups of 4.3 to that. And adding these together, I got 8.6. So 8.6 plus 430 is 438.6. Okay, so the next part, equal quotients for mental calculations. You can multiply both numbers by the same number to make it more convenient. And if you want, you could even write it like this to see it's, you could write it as a fraction, as long as you do the same thing to both numbers. So maybe times 10 times 10. Remember 10 over 10 is just 1, so that's why it works. But here, just ask yourself, well, what would be a convenient thing to multiply these by? You could multiply them by a power of 10. You could multiply, another thought that I had too is multiply this one by 4, since 2.5 times 4 is 10. And then this one times 4, that's not too bad. 20, 40, 60, 80, and then 4 ones is 84. So 0.84 divided by 10. And the nice thing about that is you can just take 0.84 and move that decimal 1 spot to the left, and then you end up getting 0.084 for an answer. Now these, just like I've said this before, but I'll say it again, the way that I'm doing it is not the only way to do it. So there's lots of adjustments that you could make, and the one that I'm showing is not necessarily the best one or the right one. It's just a suggestion for you to see. So with this one, 50, I would love it if that was 100 because it would make the dividing easier. So if I multiply that by 2, then I'll multiply that one by 2. So 34 and 34 is 68.68 divided by 100. Now I just have to take the 0.68 and move the decimal 2 spots to the left for 0.0068 as my answer. Okay, compatible numbers. So compatible numbers, remember those are numbers that make number pairs that make nice even answers. This is helpful here when you replace the decimal by a fraction. Sometimes it can make it easier. So instead of 0.25, as if we write it as 1/4 times 800 over 1, then we can see here that we can cross cancel. So 4 goes into 4 once, it goes into 800 twice. 1 times 2 is 2, so the answer is 2. And that's a lot simpler then, oh, you know what? Nope, it's not 2. That wouldn't be possible. There's a lot of quarters there. I missed the zeros, going too fast. So 4 goes into 8 2 times, but then we have these 2 zeros on the end, so that should actually be 200. So 1 times 200 is 200. That makes way more sense. I went back and I always think, does this make sense? And I think about how small a quarter is. Would there be 2 of those into 800? That doesn't make any sense, but 200 of them, that makes more sense. So, or you could think of it as a quarter of 800, or 800 divided by 4 is another way to think of that one. So this one, 0.125, that's 1/8. So 1/8 of 24. So we could also do it that way. 8 goes into 8 once, it goes into 24 3 times. 1 times 3 is 3, 1 times 1 is 1, so you end up getting 3 for that one. Okay, so for rounding, approximate each product mentally by rounding each number to the nearest whole number. So 4.6 is closer to 5 than it is to 4, so I'm going to say that's approximately 5 times 8.21 is closer to 8 than it is to 9. So this would be approximately 40. So this number would round, it's closer to 10 times this is closer to 6. So I don't want to put equals, I want to do squiggly equals because that means approximate, so approximately 60. And then I could also use front-end estimation. So that's the same thing we've done before, although we haven't done decimals, but it's the same concept. So you just take the very first number in the decimal, and it doesn't matter if it's a number to the right of the decimal or left, just the very first number you see. You're going to keep that one and make all the rest zeros. We keep this one and make the rest zeros. So 0.1 times 40. 40, so that means move the decimal one spot left since we're multiplying by a power of 10. So you're going to get approximately 4 there. And then this one, this is a typo. It's actually the same thing, so we can just skip this one since it's the same problem that we just did. And then lastly, we've got 3 problems left. Compatible numbers for approximation. If you're approximating and you notice that the numbers that you're given are really close to a more convenient substitution that would work better, then do it. So 0.26 is really close to 0.25. And then if I wanted to, I can make that into a fraction, and I could use my fraction rules. Keep it, change it, flip it. 6 times 4 is 24. That saved me a lot of time compared to if I actually had to longhand do 6 divided by 0.26. And remember, I actually shouldn't put an equal sign there. We should do squiggly equals because we approximated. We changed the 0.26 to 0.25. And then over here, we've got 0.35. That's around a third. And then you can 3 doesn't go into 268 evenly, but it does go into 270. And so 3 goes into 3 once, it goes into 270. Well, 3 goes into 27 9 times, and then add a 0. So we could say approximately 90 on that one. Let me just write that out a little bit better. So I did that problem down there. And then lastly here, gosh, there's multiple ways you can do this. You could certainly round to the whole number. So you could do like 28 minus 2 would be fine and get 26. The other thing you could do is you could change this to 27.7 minus 1.7, you know, or 28 minus 2. Either way, you actually end up getting 26. So I think this one without the decimal is easier, but either one of those are a great way to do that one.